Speak something.
Testing, testing. You guys hear me well?
Yeah.
It's a bit low. I can yell.
1 minute. I'll keep it a little bit. Yeah. No.
Testing, testing. Physics has been solved. Can you hear me? No?
So for asking questions, can you use the microphone? This one. Because you work in the hall.
Comfortable.
I'm okay, I'm okay.
Just a minute.
And the recording can capture up until this line. Please.
So hi everyone, welcome to the ICTS String seminar. So today we have Ahmed Almheiri, who will be talking to us about the final state proposal, making sense of measurement probabilities.
Thanks a lot. Let me begin by thanking Smita and Rajesh for inviting me to give this talk. It's always a pleasure to visit India. Something I find very amusing about this place is that no matter where I am in India, if I just stand outside and close my eyes, I could swear that I'm in the middle of a rainforest. But then I open my eyes, I'm in an institute. It's really great. It's always fun to be here. And it's always, most fun aspect is to meet all of you guys. And some of you know, I'm recently a professor at NYU Abu Dhabi. So for the foreseeable future, I'm going to be a neighbor to you guys, and hopefully I can visit you very often and invite you also to come by. Okay, so this talk is a black hole information talk. It's about the final state proposal. I'm going to review what the final state proposal is, and also talk about some of its sort of confusions. Something pointed out by Raphael Bousso and Bousso-Stanford is that when you have a system with a black hole with a final state projection that happens inside the interior, measurements somehow don't make sense, or probabilities of measurements are weird, and I'll explain what I mean by that. Most of my talk is going to be about this topic. I should say this is a work in progress with Ven Chandrasekaran, who unfortunately we lost recently. I don't mean he died. He switched to machine learning. So that's going to be most of my talk. At the end, I'm going to give a little teaser for how to generalize the notion of entropy to the situation where you have a final state, a projection, or a post-selection in your system. This is work in progress with a student at NYU, Yushin. Okay, so review of the final state proposal. So this is a proposal by Horowitz and Maldacena a long time ago. And it's a modification of the physics of the black hole interior, whose task is to take the inside information of a black hole, or information inside a black hole, and to transmit it to the outside. That's the task. Let me draw a picture. So imagine we have a black hole that looks something like this. It was formed by some collapsing matter in some state, so M for matter, in some state I. And what one wants is that the dynamics of quantum gravity somehow maps the state of the infalling matter into some outgoing state of the Hawking radiation, R labels radiation, where psi is related to I by some unitary S matrix S. Okay, so this is unitary. Okay, and this is want. We want this. Famously, as Hawking showed, this is not what you find. This radiation is in a maximally mixed state. What that means is that its density matrix for simple toy models, you should think of it as literally just being 1 over the dimension of the Hilbert space times the identity matrix. Okay? So there's no information in the radiation. And Hawking derived this fact by showing that the Hawking radiation coming out of a black hole is entangled with partner modes behind the horizon, and they purify each other in this way. So what this line is supposed to represent is that this qubit or this mode is maximally entangled with this mode, and so on and so forth. And so when you trace out the interior of the black hole, you're left with a mixed density matrix. The idea of Horowitz and Maldacena is to suppose, so the idea is that you suppose that there is post-selection that occurs at the singularity. It's not really understood what these words mean at the singularity, but the mechanics of what you need will be clear. What they imagine happening somewhere inside the black hole, that a projection happens. There's some state F which acts on M and R tilde. R tilde, so let's call, so this is R as we called it. Let's call the radiation system inside the black hole R tilde. So there's some projection that occurs on these two systems, which looks something like this, phi d, where phi d here is the maximally entangled state. What I mean is that, so So this is on M and R tilde. It's some state where the subsystem M is maximally entangled with the subsystem R tilde. Both subsystems are of the same dimension, and the density matrix of either one is maximally mixed. Okay? Think of just the EPR pair. So that's not the only thing involved. There's also some unitary matrix SM tensor the identity on R tilde. And because this is a projection, projections don't preserve probabilities, they don't preserve norms. So you need to actually renormalize this by multiplying by D the dimension of the radiation Hilbert space or of the black hole Hilbert space. I should have said this at the very beginning. Please interrupt me if I go too fast on anything, and just slow me down with questions. Okay. You can draw a circuit diagram to make it clear that the information has actually gone from the inside to the outside. So let me draw it here. We start with the state of the matter that formed the black hole, that's I.
Hi, Ahmed.
Yes.
Could you just explain again what's going on up there with the projection? What is F and what is phi D?
It will be clear in this circuit diagram that I'm about to draw.
Okay, thanks.
Okay. So we have the state of the matter that's represented by this I and some line here. And imagine we have, well, you can draw a set of maximally entangled some bipartite system, which we call let's call it the phi D of R tilde R. So this is supposed to represent the entangled state between R tilde and R. Let's multiply this by 1 over square root D. This is just a statement that phi D is equal to sum 1 over square root D I something like this. And the way you represent F in the circuit diagram is the following. So there's also a phi here that you project with. S here is some unitary matrix here. And so let me label things. This guy here is F. And if you contract all the lines, this gives a path for I. So if you can just sort of straighten out this line. This gives a path from the input I here to the output over here. And when I propagates through the circuit, it picks up a unitary transformation S. And so you end up with S acting on I. And you should think of this as a state of the radiation R. Does this picture make things clear? Clear for at least for the person who asked the question?
Yeah, so is it basically being teleported?
Yes, that's all this is.
Mm-hmm. Okay.
It's just being teleported from this system to that system.
All right, thanks.
Okay. Let me make some comments. So this is basically the entire proposal. Let me make some comments about this. First, okay, this is not that important, but this is a picture that maps. This is the S matrix of the black hole from when it's a transformation from when the black hole was formed to when it's sort of completely evaporated. You can draw similar pictures or generalize this for the case of sort of partial evaporation, but that's not going to be important for this talk. Yes, please. This thing here? It just means that it's in a, let's say, a Bell state. So suppose you have 2 qubits. we represent 0, 0 plus 1, 1 by saying it looks something like this. Or this is just a diagrammatic notation to say that the state of this system and the state of this system are the same. And exactly. And so you're meant to sum over all possible states of these two systems where they are the same quantum states. So here, 0, 0 plus 1, 1 plus 2, 2 plus 3, 3, and so on and so forth, depending on the size of your Hilbert space.
So that junction is a mixed state.
That junction is a maximally entangled state. Yeah. Let me just clarify that there are two notions. So there's two maximalies here. There's a maximally entangled state, which is a pure state. There's a maximally mixed state, which is a sort of a density matrix that has maximal entropy. Okay. Yes.
If you talk about the integral systems, S is a unitary matrix, and if you talk about how it will look like in, let's say, Fox space representation of infalling matter, and
For example.
we can find out.
I don't know about finding out easily, but abstractly, yes. Okay. All right. So an important comment about this protocol is that, so this is something pointed out by Lloyd and Preskill, that it's fragile. What do I mean? It's fragile to interactions that happen inside the black hole. So let's imagine that you fall into the black hole, and then you do some sort of unitary rotation, which acts on the radiation and the matter at the same time. Okay, so it rotates these two amongst each other. That's like going in this circuit diagram and inserting some unitary transformation here. Okay, when you do this, the success probability of this measurement actually goes down. Like it's important. Let me see. Yeah, it's important that in order to have this unitary relation between this input and this output, that these two systems are decoupled from one another. You can show, let me see if I can do it quickly, actually. For example, something you can do. So this thing projects on a specific state. Okay. You can do a unitary rotation here, which actually puts you on the sort of orthogonal subspace of this state. And so when you do this projection, you can get 0. So it'll just fail outright. So the only way for this idea to work is to conjecture that you're not well, one way is to say that you don't allow interactions, but that's actually that's unphysical. But one way out is to suppose that the final state is random. So this projection that you do here, so here I consider it a very special state. Okay, but you can imagine that what F is some random state drawn from the Haar measure on M and R tilde. Okay, and if you do that, then you find that this protocol is robust up to order e to the -1/g Newton sort of effect, non-perturbative effect. And here what I mean when I write this down, I just mean it goes as 1/d, the dimension of the Hilbert space of the black hole. Assuming you're only allowed simple interactions. Meaning that this unitary transformation that you might want to implement here is, if you were sort of to represent it in terms of a circuit diagram, it's going to be of length that is at most sort of polynomial in the dimension of the Hilbert space. Okay, so the idea is that this is a random state. It's a state that you can generate via a quantum circuit with local gates that is of length exponential in the number of qubits, and exponential number of qubits. If that's the case, then you cannot, you can't sort of go orthogonal to the state in the way that I described here, using a polynomially sized circuit here.
Can I ask?
Yes.
So here, like this, I'm trying to understand the statement. The understanding is that the S doesn't depend on these interactions, the thing that you are drawn in this pink box.
But
The
S
S
doesn't.
is just chosen once for all. Is that the,
S is presumably the thing that quantum gravity gives you.
okay, so there's some operator which then doesn't depend on this, on the state or anything.
Correct.
Like,
The-
or any unitary that acted before, basically.
S will depend on the microstate of the black hole. It
But-
should not depend on the operation that somebody falling in.
But if you did something, shouldn't it change the microstate? I mean,
Yeah, exactly. No, I was going to retract what I said. If you jump in, well, so we don't believe in free will. Okay, so you jump in, and you have now rotated the microstate of the black hole to a different microstate,
yes.
and that operation will now give you a different S because you're in a different microstate of the black hole.
But this fragility is the statement, even if I allow myself to change S whenever I put a unitary.
Yeah, you will change S, but it will still be unitary up to non-perturbatively small corrections. That's the claim.
What I'm saying is that even before you put the random final state, okay, this Lloyd-Pascal point, the point that Lloyd and Pascal made, is this true? What are the assumptions they are saying when they say it is fragile? Are they assuming S is independent of any interactions that happened before? They're assuming-
This fragile statement is a statement about you allow for any complexity of unitary transformation that you do here.
And then you just assume that S is independent of that transformations.
Correct.
And then the statement is that in general, you can just get zero.
Exactly.
But if I allow S to depend on it, is there a way to just get rid of this?
It's not. I think the answer is no, because S here by definition only acts on one subsystem.
Right.
So you cannot really achieve the more general thing of acting on both systems.
Maybe this is also what you're saying, but if I allow some kind of a unitary to act on the pair just before I project.
Yeah, so you can always undo things that you've done, but that seems a bit too weird.
Yeah, but I think what you're saying is equivalent to just saying that I just apply a very complicated unitary operation of very high complexity just before I project.
You can think of it like that, but it's something that quantum gravity does for you. It's not that
yes,
somebody
yeah.
did.
And then, like the statement is that I will then not get zero because any state will just be taken to something. It will have some component.
Yes.
So, what was the rationale for the original proposal that you make that this S depends only on the matter part, that it has this product form?
Yeah, the original proposal just wanted they just wanted the simplest way to ensure you have a unitary. That's it.
But it's sort of, there's no way to physically motivate why that S should act on, because it seems a little unnatural.
I agree. Yeah. I don't recall them making any comment about this in the original paper. Yes.
So I didn't quite understand what the interactions are that will break this projection. So of course, before matter falls in, there's no black hole, so there's no radiation. So should I think of the interactions between the matter and the radiation as late infalling matter interacting with early radiation that makes this thing fragile, or?
Yes. Well, late infalling experimenter that chooses to do an operation on the interior modes in combination with the matter that form the black hole. They have enough time to get a piece of both, as you make that assumption.
I see. Thanks.
Okay. All right. So for the remainder of the talk, I'm going to consider a slightly simplified model of this. So I'm going to draw the following picture. Let's say you have one pair of modes. Let's say it's a qubit system, just of a two-dimensional Hilbert space. And an R tilde, which is entangled with R. Okay? So now I'm imagining that my entire system is composed of these four subsystems. Okay? You can think of this as, so you get something like this if you imagine that your initial matter that formed the black hole has been maximally entangled with some reference system, for example. Okay? The state on this slice, I'm going to call psi, which is phi 2, so the maximally entangled state of B tilde, or B tilde B, times phi d R tilde R. Okay? By unitarity, what we need is that B R is in a pure state. Okay? Something that we expect sort of on general grounds, by which I'm going to assume, I'm not going to prove, that the density matrix of little b is maximally mixed. The rationale is that you have some sort of quasi-random state of all of the radiation, and if I separate a small subsystem from that, I expect it to be maximally entangled with the remainder of the system. Okay. Okay. For this to be the case, one actually needs the following condition. So for this to be, let me say this is equal to that. One needs the condition on the final state, which is the following, that if you were to trace R tilde, F, so here F acts. If you were to trace R tilde from this, so let's call this rho B tilde F, which diagrammatically you can represent as the following. What we need is that this is proportional to delta ij, so it's identity, times d. Okay. Notice that this is it's not a normalized density matrix. Okay. Okay, one more picture that I'm going to draw on this side. Oh, sorry. Yeah, you're no good. This is meant to represent the final state. Okay, so I have this density matrix here, which is just this. Now I've traced R tilde. Your blackboard is magnetic, right? Okay. Okay. So the circuit diagram for this is just something like this. F B R Okay, so the pure state on BR is prepared by projecting on B tilde R tilde. And this thing I'm going to call the state is just this. Okay. Okay, so now let me switch gears and talk about the AMPS experiment. Okay. In this context, the claim is within this final state scenario, you can avoid the firewall paradox or the AMPS paradox, and you can have both unitarity plus no firewall. Sometimes just, well, I'm going to call this a no drama situation. Let me remind you of the AMPS paradox. Again, let's imagine you have this black hole formed from some matter. The problem is that by unitarity, this mode, let's call it B, has to be entangled with all of the early radiation. I guess I don't need to call it B. So you need this entanglement for unitarity. But in order to have a smooth horizon, one needs that these two modes are entangled. So this is for no firewall, or let me call it no drama. But entanglement is monogamous. This mode cannot be both maximally entangled with two separate systems. Okay. Okay. Now to assess whether we actually have, to assess whether this claim is true or not, what we need to do is well, one thing you can do is you can consider compute the probability that a measurement on the various systems actually, what does it give you for the entanglement between B and R, or for the probability of finding that B and B tilde are entangled. So I'll go through that in detail. So the relevant measurements are the following. So to check for no drama, the measurement one needs to do is, let me call it pi B tilde B, which is just to check that the two modes, qubits or whatever, are in the right entangled state. Okay, I guess I've been drawing it like this. Okay. So this is the projection operator that projects B tilde onto the maximum entangled state. To check unitarity, what one needs to do is to check that B and R are in this pure state. Okay. So the projection is just the following. So this is pi B R, and it's 1 over 2D. Okay, so this is pretty trivial. Okay, it's just to check that B and R are in the right pure state. Okay, so these are two measurements that you can do. So you're an infalling observer, you can just do this measurement. And so now what we're going to compute are the probabilities of that. Sorry. Okay. This pi here is it's a result of a measurement. Okay. So you can say you measure B and B tilde in the maximally entangled basis, where this state is one element of that basis. And what we're going to compute is the probability of finding B tilde or BR in those respective states. The way to do this, well, let me first remind you how this is computed in standard quantum mechanics without a final state, and then we'll put in a final state. The probability of finding this result, of finding any result, probability of some result is just the expectation value of the projection operator onto that result. In the presence of a final state, this thing needs to be modified. The modification is to you square the projector. We know that pi squared is just pi by definition of it being a projector. But then in the middle over here, you put in the final state, some post-selection that happens sort of in between. So suppose, this thing prepares some pure state of B and R. Okay. When you suppose you measure, you want to know what the state is on B and R. Okay. One way you can do this is you pick a basis for B and R, and you consider you have a pointer system, and you consider a unitary transformation that, depending on what the state is of B and R, the pointer points to one of the given possible basis states. This is one of those states. So I want to know what is the probability of finding B and R in this state. Hopefully that was clear. Like, for example, suppose I have 2 qubits, and I want to know what's the probability of finding the 2 qubits in the state 0, 0. Okay, what you have to do is the possible outputs of the measurement are 0, 0, 1, 1, 0, 1, and 1, 0. The probability of finding it in the 0, 0 state is just what I did here, where this is 0, 0. Yeah, this is how it usually works in quantum mechanics. Now, the modification in the presence of a final state is that you put this, you double the projector, and you put this final state in between. The picture for this, okay, so let's actually compute the probability of these 2 measurements. Let's first compute.
Sorry, Ahmed, just
one sec. Yeah.
One question. So the first line that you've written down, now
Yes.
if I had a set of pies, projectors, which
Okay.
kind of added up to 1
Yes.
identity, then it's clear that the probabilities of all those projectors adds up to 1. Right.
You're asking me in the case of the final state.
Yeah. So at least I can see how that happens in the first line.
It definitely
which is
happens on the
usual.
first line. Yes.
Yeah.
It also happens on the second line if you normalize your final state in the right way. If the final state is normalized in the right way, then yes.
Yeah.
Like,
So
for example, this D here.
So the statement is that if I normalize my final state in a certain way,
Let me see.
so I have a set of pi alphas, so that sum over alpha pi alpha is 1. Now you're saying that the probability of pi alpha sum over alpha would also be 1. If I just normalize f in a certain way, how do I see that?
I see. You're asking, for example, so we put an I here, and an I here.
Yeah.
Your question is that if I sum over I, do I get 1?
Yeah.
How do I see that?
So in the usual quantum mechanics, I get 1. That is just the first one. You just add up. It's just psi being 1.
Yes.
So how do I see that here?
I don't have a quick argument. Well, yeah, it does seem like in general it should not work. But thankfully, in the case that I'm going to describe, all I can say is that I've checked that and it works. But maybe we should we'll come back to that later, maybe. Or we can talk about it.
Can I also ask a question? Can you hear me?
Yes, Subrat.
Yeah, hi. Okay, great. So maybe I should have asked this a little earlier, but the philosophy of the original proposal was, we can basically do whatever we like in the interior, right? So we can impose this projection and it teleports information outside.
Indeed.
However, I think this assumes that there's some factorization between the inside and the outside, and we now know that's a bad thing to do. Now, in these more recent, in these page curve computations, of course, as you know very well, the way that's made precise is by coupling things to a non-gravitational path, and then things factorize between one part of the path and the other, or the CFT and the path. So if one were to, try and do that for the final state proposal, what would the proposal be that we're imposing a final state on the CFT? Because we can't just impose it in the black hole interior. So are we imposing it on the CFT and part of the bath and then allowing teleportation, or what are we doing in a more precise setting?
Yeah, unfortunately, I don't have a good answer for you. Let me just make a comment that I'm not trying to find the ultimate theory of the bulk. This talk is going to be mostly about aspects of the Horowitz-Maldacena proposal and observations of Bousso-Stanford, and ultimately how inspiration from replica wormholes resolves that. But it's not obvious that this is the correct final story. So unfortunately, I don't have a good answer for you. It's not obvious where the final state acts in the bulk, if it does at all. The most precise statements made about the role of a final state-like thing has been this paper of Harlow and friends about trying to say that there's sort of a truncation or a projection that happens once you consider sort of the mapping between the bulk Hilbert space and the boundary Hilbert space. But unfortunately, I don't have a better answer for you at the moment.
I see. But we don't want to impose it on the CFT. You're not saying that, in the CFT coupled to a bath, on the CFT part of the Hilbert space, we should impose a final state. That I guess you don't want to do.
Well, the only thing I can say the only projection-like thing that happens on the CFT side is actually something that we do all the time. Suppose you consider a set of states that are prepared by some Euclidean evolution, e to the minus beta h. And you imagine along this Euclidean preparation process, you imagine you act along the way with some operators, OI. Suppose these operators, OI, are a set of orthogonal, suppose that they prepare orthogonal states in the CFT. It's definitely a fact that after some Euclidean evolution, those states need not be orthogonal anymore.
Sure, right.
So there is something like, I would say this is the closest thing to a projection-like thing that happens on the CFT side that can prepare for you some overcomplete set of states in the CFT, which is kind of like this is the closest thing to a final state that I can describe.
But this is what helps us cut down the size of the bulk Hilbert space. I see. But here, I thought you want to impose a projection even within the correct set of microstates, right? Or is it projection in this bigger space?
The reason why I bring this up is because those two things are intimately related. Because the replica wormholes, for example, as we know, they give you sort of a correct accounting of the number of states of a black hole, correcting the naive semi-classical picture. And furthermore, the results of the replica wormholes can be actually reinterpreted as having a final state that happens somewhere, maybe where the island is, but where it's a random final state that you average over. So I think these two things are intimately related.
Okay.
Yeah, but perhaps we can talk about this more offline when you're here, maybe tomorrow.
Okay, great, yeah.
Sorry, could you just, so this is a statement that is a calculation that the replica wormholes, you're saying can be interpreted in the final state?
Yeah, it can be interpreted as having a random final state that occurs where the island is. I will touch on that a little bit later.
Okay.
Okay. All right. So let me quickly just compute these probabilities. Okay, so I'm basically going to do this, where I project here with the pi's either for this guy or this guy. First, let's do the no drama, the no drama experiment. So, no. The first line is the standard quantum mechanics, but the second line is what you have when you have a final state. It's the generalization of the first sentence, of the first line in the presence of a final state. Okay, so I'm going to just do this one explicitly. So you first start with, let me also say that I'm going to represent these lines like this with just this. Okay, keep that in mind. All right. So the state that we're considering looks something like this with a projection. Okay, good. But now what we want to do is we want to do a measurement pi. So up until here, this is the state psi. Now we're going to act with the measurement on B and B tilde and B. So that's going to be represented by the following. Okay, so there's a measurement that happened here, and you have to multiply by 1/2 because of this 1/2. So, and then you tack on the final state, and then you compute the norm squared. Okay, so I need to copy this diagram again. So that's going to look like this. Okay, so there's a 1/2 here. There is a 1/√2d, a 1/√2d, and let's use this relation here, this condition on the density matrix. If you do this, and you track, so let me color the R tilde with orange. So that's this thing here. What it does is that it attaches this line to this line. Okay, so the picture you will get is just the following. Now there's a factor of 2 here, factor of 2 here, factor of 2 here. There's a 1/2, there's a 1/2. There's an overall factor of 1/2d, and there is a d coming from the orange line, and this is equal to 1. Good? Okay, awesome. So this tells you that you have no drama with probability 1. Okay? Then you can do the same thing by computing probability of unitarity. the picture is just the following. I'm just going to draw it, but I'm not going to simplify it. No. So there's something that looks like this. This guy is the projection by pi br. This is the projection pi br, and this is the final state. And this might be obvious to some of you. This is also equal to 1. Okay, so indeed, the probability of there being no drama is 1. The probability of unitarity is also 1. But then what Raphael and Douglas pointed out is that if you compute the joint probability where you first the probability of first checking that you have unitarity, and then checking that you have no drama, then you get a very, very different picture. Then the answer is not equal to 1. Let me.
Sorry. So this means you're taking a product of the projectors.
Exactly. So what you're doing is you start with the state psi, then you act with pi br, then you do pi b tilde b, and then you project. Why am I choosing this ordering? This ordering is the physical sort of ordering, because that's what an infalling observer, that's the order in which an infalling observer is going to check these measurements, or these measurements. They're first going to check that these two are entangled, and then they're going to check that these two are entangled. Let me just draw the picture for this part of the circuit. It's something like this.
Probability is the mod square of this, right?
Can you say that again?
Is it a mod square of this?
Exactly. The probability is the mod squared of this.
Okay. So you calculate the mod square.
Yeah. Let me just draw this part of the circuit. This is exactly what I drew down here. This part is this measurement. And this part is this measurement, okay? If you compute the norm squared of this, you find 1/16, which is very different than 1. And so this is crazy. What this says is that the probability, 1/16 is 1/4 squared. Sorry?
For the norm square, you just put the
Yes. Exactly. Exactly. So 1/16 is 1/4 squared. Each one of these 1/4s tells you that each of the measurements is completely random, right? The result is completely random. But we just computed here that the probability of, let's say, the unitarity measurement is just 1 by itself. So it tells you that having made the choice that in the future you're going to do a different measurement, affects the statistics of the now measurement. Okay, so there's a causality here. Yeah, so the presence of the final state induces some kind of a causality. So this is a causal.
But wasn't the final state proposal itself in some sense a causal?
Correct, but the hope was that quantum gravity does something which might look acausal to us, but all simple experiments that you do, not even simple, any experiment that you do would not detect any acausality. But here it does detect it. Because having just made the conscious decision that in the future I'm going to measure something else affects my result today. Okay, so this is the problem. And I claim that there's a mistake somewhere. Okay,
Shouldn't the final state depend on it shouldn't depend on the measurements. I mean, the final state is supposed to exist independent of, it's just a state of the black hole. I mean,
correct. But
so it's independent of what kind of measurements or anything some observer falling into
it could depend on this is kind of part of the discussion we had before, that the final state, you can imagine that it depends on the microstate of the black hole. If you choose to jump in and do something, you've changed the microstate. But here, how does physics know that I'm going to jump in after I do this measurement? Right? I guess what I'm saying is that this acausality is really bad. Like, nothing of the sort that you're describing, where the final state sort of accounts for what you're doing when you jump in, can fix it, because the result is something that happens before you jump in. This might not be a completely satisfactory answer, but let me show you another way of resolving this. Okay. The resolution is that, one thing suspicious in this calculation that we did, I think is in fact what Suvrat was getting at, which is that nothing here seemed to be sensitive to this idea that the interior of the black hole can be encoded in the radiation. Okay, so it's insensitive to where should I write this? To B tilde being part of R. Okay, and let me now draw some inspiration from replica wormholes, the results from replica wormholes, and then come back to this and tell you what the fix is. But before I do that, how am I doing on time? How much time do I want? Yeah. That's a dangerous question to ask. Okay. So
maybe a quick question. So instead of like calculating mod square of this, let's say if I did a final state projection in between the measurement.
So if you did a final state in measurement between the measurements.
Yeah, it says that I put an FF inside that.
But
I mean,
but it needs to be final.
Yeah, so in the sense that so this is something also maybe I should have asked before. In the original Horowitz-Maldacena proposal itself, the singularity is teleporting. Okay, the
singularity
is quantum teleporting the interior.
Yes.
Does it, like it probably does it all the time, right? I mean, it's not completely clear. Does it do it like in one?
Correct. It's not obvious.
Or does it continuously do it as things fall into the singularity? Because things are continuously falling into the singularity.
That's right.
It's difficult to say when is it falling in because it's not clear. But the point is that but is it continuously doing it in that sense? Like there may be a continuous post-selection at every measurement in some sense. Would that help? If
there is a way to think about something like that, but you have to sort of. So here, all these pictures are drawing sort of the completely evaporated case. So you're not sensitive to the statement, but if you were to put back in the black hole degrees of freedom, in some sense, what happens is, so remember, so we said that in the situation where you have a random final state, okay, this might be a cryptic comment, I'll just say it and then we can discuss more afterwards. You can imagine just adding a random unitary that happens here. It turns out that there's a way of thinking about this as at any sequence, at any point in time, if you want to recover what the state is of the radiation, you then put in a final state that happens at that time, somewhere inside the black hole. But then suppose you want to evolve the system in the future and reproduce what the state is in the future, you first actually undo the final state that you did, evolve a little bit, and then do it again. But we can talk about this more afterwards. Okay, so inspiration from replica wormholes. Where should I go? Here? Okay, so from replica wormholes, we learned that non-perturbative effects can give you the page curve. So then you can ask, okay, fine. Suppose I set up the problem in this way and then take into account non-perturbative effects. Are those going to fix the problem? It turns out that it's not quite as simple. You need to implement a different protocol, a different measurement protocol that gives you sensible results. I'll explain what that protocol is in a second, but let me first just make a quick comment. The replica wormholes, you should think of them in this circuit diagram as doing the following. So we have these final states F here, here, here. You're meant to average over this F. If you average over this F, what that implements are, let's say, Wick contractions between the different Fs. That sum over Wick contractions, those are the non-perturbative contributions. Okay? It turns out that it does not change the story if you just do that. You need to modify the circuit to get a sensible answer. Let me now just discuss how replica wormholes implement this statement. Okay, I'm going to consider the West Coast model, and I'm going to be very quick. Suppose you have the following. Let's consider the following situation. You have. Let me consider the following black hole. This is a single-sided black hole. This is the asymptotic ADS boundary. I want to think of this region here as an end-of-the-world brane. Okay? Let's imagine that this end-of-the-world brane comes in many species, and it's entangled. Actually, before I do that, one can prepare the state by a Euclidean path integral in the following way. Okay, so here's the end of the world brane. This is Euclidean and this is Lorentzian. Let's imagine that this end of the world brane comes in many species, and let me consider the state where this end of the world brane is entangled with some reference system. The reference system you can think of as the radiation outside, and the end of the world brane inside the black hole as like the interior partners of the Hawking radiation. And the boundary system, let's call it B. The state here is, let me call it psi, which is sum from I goes from 1 to k, where I labels the state of the end of the world brane. So for each I prepare some state psi I of the boundary, and I'm entangling those states with some reference I. Okay? And there's some k here, which I'm going to take large. This point here is where the event horizon of the black hole is. Let's consider let's consider these a so-called code subspace of states where I act somewhere with an operator which inserts some matter particle in the state A. Okay, so let me put in this label here. Okay, so this state psi A prepares for you a black hole that's entangled with its radiation, and which has a particle somewhere in the interior in the state A. Okay, all good. Let's discuss how to, the operation that you can do on R, the radiation, that allows you to change the state of the interior. Okay, those exist, shown by Pennington, Stanford, Schenker, and Yang. You can write down which diagram do I want? You can write down an operator, let's call it OBA, which does something which can be expressed in the following way. This is an operator which it acts only on R. So the only open indices here secretly are just these two. Okay. The reason why I'm drawing the interior as looking something like this is because I'm actually skipping a lot of steps. And what I'm going to show you is how this operator OBA, when acting on the state psi A, produces for you a state psi B. Okay. The way that it does that is the state psi A. So here I'm drawing this the full space time. This is not just a state. This is a state and its evolution. The state psi A is really the state at t equals 0. Okay, so that's what I mean by the state psi A. Now, let's imagine acting with OBA on the state psi A. The picture that you're meant to draw is the following. Let me see, what am I doing? Oh, no. Maybe I should use a color. Oh, sorry. So this is the state. I've contracted the two radiations. The radiation part of the bra of the operator gets contracted with the radiation in the ket of the state. The result of doing this is actually, really the way you should think about it is that it projects, roughly speaking, this part with this part, okay? And what it leaves behind is the ket part of the operator. So notice that the ket part of the operator is literally psi B, okay? So this thing cancels this thing, and the A here contracts with this A, and what you're left with is the B. Okay? So this is how the state psi B is generated by acting with this PETS operator. The upshot here is by doing an operation on the radiation, you've replaced the interior of the original black hole with an interior that came from the operator. Okay? Now let's go back to this picture. And let's look at pi BR. When pi BR acts on BR, the bra part of the operator the bra part of the projector contracts with the state. Right. So, for example, this was the state, and the bra part contracted with it. You're meant to then ignore this part. So this has been projected out now. But what remains is this part of the operator. So the idea is that if you were to look at, let's go here. So what I'm writing down, what I'm going to draw right now is BR acting on the state psi with a final state here. So, or let me. The thing to notice is that this thing here is what we were calling R tilde and B tilde, which came from the state, but there's also an R tilde prime and a B tilde prime that came from the operator. So this is in the Bousso-Stanford calculation. Here, one does this projection, but then, so this is the BR measurement, but then when one comes to do the B tilde B measurement, they compare B, or they do the measurement on B and the original B tilde, the P tilde from the state. But from this replica wormhole story, because you've replaced the B, well, after you act with this operator on the state, you introduced a new interior, and the B tilde that you're supposed to be acting on is the new B tilde, which I'm calling here B tilde prime. So the statement is that the picture is the following for the two measurements. Two measurements are represented by this. So this is the pi B R measurement. And this thing here is the pi B tilde B measurement. So these two pictures are qualitatively different. The pi B tilde B measurement is now a subsystem of the pi BR measurement. And then if you do this and you compute the probability, you just get 1. The reason being is that, well, this pi B tilde B measurement, it acts trivially. The state was already entangled in B tilde B was already in the right entangled state. So when you acted this projection, you just leave it the same. And so this does nothing. And we already checked that the probability of finding it in pi BR is equal to 1. So the answer is 1. So the idea is that the lesson that we get from replica wormholes is that upon doing this measurement of B and R, you introduce a new interior, and then it's in that new interior that you have to do the second part of the AMPS experiment. So that's the main punchline. I was going to talk about entanglement entropy, but maybe given that I went a bit too far, maybe I should. Well, first let me take questions.
Okay, so from this diagram, it looks like if you can do the pi BR measurement,
Yeah.
you already know about the pi B tilde B measurement.
It's not that you already know about it. It's just that the correct B tilde that you're supposed to include in the second measurement is something that's introduced by the pi BR measurement. Right? So going here, there are two possible interiors, two possible places on the circuit diagram that you could have called the interior of the black hole. Is it this one or is it this one? And the Bousso-Stanford is they used this one as the interior, and the claim here is that you're supposed to think of this as the actual interior.
You can go on.
I'm going? Okay, good. Okay, the second part will be brief. Yes, yes.
It's a question perhaps right in the beginning that the Maldacena and Horowitz-Maldacena proposal had to do with the fact that there is a singularity, semi-classical gravity. So
time ends at some point, yes. The time ends somewhere.
yes, but I mean, in a sense, if I think that I'm ultimately embedding everything in string theory, and there are no singularities.
Well,
The status of this final state proposal.
So the question was, in string theory, singularities have to be resolved. So does that mean that the singularity in the interior of let's say a Schwarzschild black hole, doesn't that mean that the singularity in the interior of say a Schwarzschild black hole is not really there, and hence we don't need to resort to final state? But I think that's too quick, because even in the case of a Schwarzschild black hole, once the black hole evaporates away completely, the entire system is outside. But that doesn't mean that there's no interior. There is still an interior somewhere in the past of the space-time diagram. But there should be a way that like time still ends there. That's not okay. When we say singularity, one interpretation of that word is that we don't understand the physics there. Okay, but we hope that string theory will teach us what the physics of that region is. However, that's not the same thing as saying that string theory will tell us that there's no end of time behind the black hole horizon. There could still be an end of time behind the black hole horizon. In fact, I find that very plausible, even in string theory.
I wouldn't know what to make out of what you said because it needs to define them. Also, I mean,
Okay.
it looks a little.
Could I just say something about Spencer's question?
Yes, go ahead, Sobrat.
Yeah, sorry. So you could draw some slice which is very close to the singularity, like in the far future in the interior. And I thought this final state was saying, we'll postulate some quantum blah blah, so that on the part of the slice that's close to a singularity, we impose some, we say the wave function is of a certain kind. That we could do even before we actually reach the singularity, right? Just by cutting off the space-time just before the singularity and imposing some boundary conditions there in the part of the interior. I mean, yeah, so what bothers me, which I guess is also related to Ahmed's talk, is that this assumes that you can factorize the wave function, but the fact that there's a singularity doesn't really matter, right? You just cut off the space-time and gravity becomes strong and impose some boundary conditions in behind the horizon. So somehow the proposal is that the right way to resolve the singularity is somehow to impose these boundary conditions. We hope that somehow quantum gravity will force the wave function to something just before you reach the singularity. Isn't that, at least that's how I thought of it. Is that not right?
Yeah, I think that's a fair explanation. But we can come back to this and discuss over lunch, dinner, and so on. Yeah, so, all right, the next part of the talk will be brief.
One question.
Yes.
So, in the replica wormhole story, there were these questions of whether are you thinking about the bulk as being an ensemble average over unitary
Good,
or
good, good.
something.
Yes, yes.
So now in the final state proposal, so now as you're saying, there seems to be some kind of a consistency between what the replica wormhole story is saying and the final state story is saying.
Assuming you average over final states.
Sorry?
Assuming you average over final states.
Yeah, assuming you're doing some ensemble average. So what is the kind of, is there a analogous question in the final state proposal? Some kind of, because in the replica wormhole story, the question would be to calculate some observables across the boundaries, in two boundaries or something, right?
Two copies.
And then asking whether things that you think are factorized in unitary, things you realize are not factorized.
Yeah.
But are there similar things that happen in this story, in the final state story?
It's just what I said. Like, let's say you consider two copies of your black hole. Okay, I have two copies of the black hole. Now I claim that in this theory, I have to average over the final state.
Okay.
Well, I'm averaging over these two, so there's a chance of them being Wick contracted. So now that's like a non-factorizing wormhole, for example.
Okay.
Yeah.
So you're saying the final state, this story also inherits this.
Yes.
Is the claim that these two are identical? That anything that you do in one, you can do in another, and so on? Or?
I mean, ultimately, it depends on the model. In this model, in the West Coast model, if I'm not mistaken, I think if you like just restrict to like planar diagrams, then I think they're like exactly the same. Planar diagrams, I mean, like when you compute like a replica from Renyi entropy, then you only consider planar diagrams in that computation. And it's exactly like having a random final state.
Practically, like at least in the replica wormhole story, the dominant things that we pick up are all planar, right? Isn't that?
So the dominant ones are?
Most of the observables one computes in the replica wormhole story.
Yes.
The dominant diagrams are all planar. Right? Why would you? Are there some observables for which?
No. Let me see.
Let me pick up non-planar diagrams.
I think you're right. So, sure, yes. But suppose you consider non-planar, then it's not obvious to me that they're the same, but they might actually still be the same because there are also some non-planar diagrams even in those contractions.
Okay.
I would refer to the paper of Pennington and friends.
Okay, so the statement is that as far as the planar diagrams, let's say they dominate over both. Here, big contractions are all planar, and there, all my wormholes are all planar in the replica story. Then the statement is that one can interpret these two things go back and forth. Is that?
I think so. But I would have to double check. But that was my understanding.
Okay.
So Ahmed, another question. Maybe it should have been clear, and you can explain more to me later. In this story, of this model, you have these end of the world brains that are entangled with this radiation region R, and this final state projection should never affect any physics in R. And is that should be true, right? Because R is just some entangled system, non-gravitational system.
What do you mean? What do you mean by it doesn't affect the physics in R? It definitely makes a prediction for what the state of R is. For example, and then naively, semi-classically, you'll think that R is in some maximally mixed state. But because of the final state, R is actually not maximally.
Very good. Yeah. So it teleports information into R. But I mean that if you make a measurement or something, it gives you would get in R exactly what you expected. I mean, apart from the fact that the information is in R, is that right? And maybe it's not a well-defined question. That you're not modifying physics in the non-gravitational region as you are in the black hole interior. Is that right?
Yeah, no, I think that's right.
Okay.
I think all. So let's say we work in the East Coast model, okay, where R is a bit more non-trivial. Then it's just going to be sort of your run-of-the-mill field theory with no exotic property. The only thing that changes is the state of that system.
Okay. Yeah, thank you.
Okay, so, all right, so let's quickly talk about entropy. Recall that when I discussed the definition, or when I defined the probability in the presence of a final state, I doubled the number of projectors, and I inserted between them a final state. So if I was to draw a picture, I suppose I have, so the way that you compute a probability is you have some state, so a probability of some measurement result, you have some state, and you consider also its brawl. And then you compute the overlap of some projection. Okay, so there's a pi here. In the presence of a final state, this thing was modified. What I did was, so you first erase, what you do is you imagine having two pi's, and in the middle, you have a final state, some final state projection. Okay, now let's imagine that we have some state psi, which is a state of four systems. Sorry, it's four systems, A, B, C, D. Okay. Suppose I want to compute the entropy of BC. To do that, I first need to define the density matrix of BC, which is just you take this and you double it, 1, 2, 3, 4, and then you trace over A and you trace over D, standard. Let me draw this picture in a slightly different way. Let me move this up and move this guy down. Then I'll have something that looks like this. Okay, so that's rho BC. But now let's suppose that you have a final state that acts on AB. So we'll have something like this. Okay, so there's a final state that's going to contract with AB on AB. I'm going to define rho BC with the final state as the following object. Notice, so without the final state, rho BC had 4 open legs. Here, I want to define rho BCF in the presence of a final state with 1, 2, 3, 4, 5, 6 open legs. So this is a proposal. Let's just check that it makes sense.
Sorry, just so AB are interior, CD.
No black holes here. Sorry, I should have said.
Okay, so what is
there are no black holes here.
Okay.
I'm trying to make just a proposal of suppose you have a quantum system where you have a post-selection that happens in this quantum system.
On only 2 of the qubits.
On a subsystem of your system. In my case here, I've split it into 4 and I'm acting on 2 of them.
Just on AB.
On AB, exactly.
Okay.
Okay.
Okay. Okay.
Okay. Now I'm so here I have some final state F. Notice that if I take this and I sum over F, some basis over F, I will get back this density matrix. Okay? Because if you sum over F, this thing just becomes the identity. And then this guy just connects straight through. This is an identity, but this is just a line that does nothing. It just factorizes. So you end up with this picture. Okay. So this is a proposal for what the density matrix for the density matrix in the presence of a final state. This might be. Let me draw pictures in the case where we have a field theory where I think it'll actually make a bit more sense. So
shouldn't you be, you have these 6 endpoints here. Shouldn't you be connecting the interior endpoint?
No, let me draw the next picture and it might be clear. Let me just draw this first. So suppose that in a field theory, you're interested in computing some correlation function of some operators. Let's say they all happen at the same time t, and you're expressing this in an formalism. Okay, the way you do this is you have a path integral that evolves up to some time t, and you have some insertions at this time. Okay, all standard so far. Suppose you want to compute the Renyi entropy at that given time. What you would do is replace these with twist operators. Let's say it's a Renyi entropy of a single interval. This would be sigma n, sigma minus n. Okay, so the picture you draw is you have two twist fields and there's a branch cut connecting them, n minus n. Let's imagine that n is even. So n is even. This picture can be drawn in the following way. Where I have now 4 twist fields, where here the twist field has degree n over 2, and here it's minus n over 2, n over 2 minus n over 2. The reason why this picture is identical to this picture is that this time evolution here really does nothing. You can just unwrap this, bring it back up, but when you do that, these 2 twist operators get closer and closer and closer. You can do an OPE between them, and that just gives you back n. Sigma n over 2, sigma n over 2 really is just sigma n. Okay, if they're coincident. Okay, good. But now imagine you insert one more fold in the middle between these 2. In particular, I'm thinking about something like this. Where here I have n over 2 minus n over 2. Here I have minus n over 2, and somewhere behind is the n over 2. But let's imagine here we insert operators, for example, or what I'm interested in doing is inserting a final state. So I'm going to consider some region here where I cut the path integral, and I put a boundary condition here, and the same one on this side as well. If I sum over I, this thing closes, and then I go back to this picture, which is equal to this picture. That's the same statement as here. When I sum over f, I go back to this. The picture here, you can imagine flattening everything. It's like being on the plane, where I have something like this. It's a 4-point function of twist fields in the presence of a boundary. Okay? The proposal is that this thing, if you compute it and then take n goes to 1, would compute for you, and then you correctly continue everything in the right way, would compute for you von Neumann entropy in the presence of some final state that happens. This is the entirety of the proposal. This is still work in progress. I'm interested in seeing what this predicts for, well, how does this entropy behave in this system in the presence of a final state? And the thing that I'm interested in doing is trying to see if I pick the right, is there a right choice for a final state here, such that the entropy that you compute via this prescription gives you something like a page curve, and does it reproduce any features of quantum extremal surfaces and so on and so forth. I imagine that in that case, I'm going to have to pick a random state here. But if I pick a random state here and I have multiple copies or n copies, choosing a random state here is going to connect the different copies in some other way. So this might become like a 6-point function of some twist fields and so on. So this is still very much work in progress, but this seems like a natural definition of how to compute entropy in the presence of a final state. Okay, that's the end of my talk. Thank you.
Thanks, Ahmed, for the nice talk. Are there any questions?
Sorry, just to understand this last statement. If you sum over I, it will just close, the hole will just close up.
Yep.
So what you really want to do is that on that hole, you want to specify a boundary state F to get the final state proposed. Is that right?
Well,
and then some random enough F.
No, the statement is that this thing would compute for you entropies in the presence of a final state. Okay, but it's
provided you don't close down that hole.
Exactly, so long as you don't close it. What the right final state to pick that will reproduce results of black holes would depend on,
So the statement is that you have that hole and then there is some boundary state there.
Exactly.
Right?
Yes.
And then you do the path integral with that.
Exactly. Like in some sense, so we know that replica wormholes, or rather I made the claim that replica wormholes is like having a final state. I want to see if there's a way to not have replica wormholes and just have something like this and see how much one can reproduce from replica wormholes. It's investigation in that direction.
There are any more questions? No, let us thank Ahmed.
When did we start? Okay.
We usually have half an hour worth of questions.
Okay.